Hello everybody, this is a video presentation presented by Lab Vision Technologies for the end user about the energy band gap of semiconductors, or basically it is the effect of temperature on semiconductor. As we all know, the conduction band and valence band are the two bands in which the electrons of that particular semiconductors used to reside. Whenever we provide energy either in the form of temperature or in the form of voltage, we will get the valence band electron into the conduction band. That is the reason for forward bias and current carrying capacity of a particular diode or a particular semiconductor enhanced by giving that energy. The difference between this valence band and this conduction band, this region, is known as energy band gap and denoted by delta E. As we all know very well, whenever we provide voltage, it starts carrying current, and in case if we are not providing voltage, if we are increasing the temperature, then temperature is the form of heat will be provided to diode. It will generate some what we call energy, and the conduction band and valence band, the band gap, the energy gap between these two will be filled up, and the electrons will start to flow in the semiconductor, and this is the reason it will carry current. One of the important term is known as saturation current, which is very important in with the regard of this experiment. Saturation current is the current at which diode starts, or the semiconductor starts carrying current, or it turns into the forward bias direction. So we are using this experimental kit, which is known as energy band gap kit, to demonstrate all these things into our syllabus, which are in our syllabus. So talking about this particular kit, this comprises first of all this thermometer, number 2 this oven, number 3 this is a voltmeter, number 4 it's an ammeter, number 5 this is a power supply switch. Here we will see something like that. It's oven which will heat up the diode, and if we want to turn it high, then the amount of heat generated will be very high. But we have used here the GE diode. This means that GE diode have the capacity to bear a temperature about 80 degrees. So taking precaution, never exceed the temperature. Always switch off the oven whenever the temperature exceeds 80 degrees to keep the kit working for a long time. And talking about the experiment is quite simple, only calculation, because we are teaching engineering students. If calculation is the only thing which is left after the demonstration, then anybody can perform that calculation. So taking a look, first of all, turn off the power switch. Will this light close? Now taking the example, this is actual voltage which we are providing. So changing this, the value of current is increasing very slowly. Changing this, value of current increasing very slowly. But right now its temperature is 29 degrees Celsius. When we turn on the oven, the temperature starts to rise. As the temperature starts to rise, it will pop up near about 40 degrees, 50 degrees, 60 degrees. As it comes to 60 degrees, the change which we are seeing, that whenever we are changing this regulator, voltage changing very fastly, but the current value is increasing very slowly. But as this temperature start rising, the value of voltage for which the value of current is changing. Now look at this, we have turned the voltage to 2 volts, 2 volts. The value of current comes as near about 15 microampere. So this is the reason that energy band gap, the energy band gap which we are used to calculate over here, is like this, that voltage, now for a recent change in voltage or a minimum change in voltage, the value of current is changing very rapidly. Look at this, look at this, look at this. The value of current is changing very rapidly as the voltage is increased near about 0 to 2 volts. The value of current changes about 50 microampere. So taking this all calculation on the graph paper, we will plot a graph. Now it's time to turn off the main supply and the oven in the low voltage. The value of current is going to be 0. By using the value of saturation current, the current at which it starts to conduct, by using the value of saturated current and the temperature at which saturated current is generated will be in the denominator of this expression, that is 10 to the power 3 by the temperature. But one thing to be noted over here is the temperature should be in the Kelvin and the thermometer shows reading in degrees Celsius. So it's better to convert it to Celsius to Kelvin. It's very easy. Just add up 273 upon I think so, nothing to 8. Just convert it into the kelvins, and after that, whenever you are going to plot a line, a graph between log of Is saturation current to 10 to the power 3 by T, you will get a straight line. If you are supposed to calculate the energy band gap, then the slope of this straight line, which is AB by BC, or the tan theta of that particular line, will give you the slope, and divided by 5.063 will give you del E, which is our requirement for the calculation. As we come to know that the value of this comes as 0.6 for my case, 0.6, and we know the value for germanium, which is the standard value, is near about 0.7 electron volts. So percentage of error is round about 1.1. So we should compare the actual results with the theoretical results. This is the main aim of this experiment. I hope this presentation was not as boring and you will enjoy doing work on our Lab Vision Technologies kit. Plus, always I should tell you some precautions. Never exceed the temperature up to 80. Precaution number 2, we are using germanium. If by the way in near future it is required to change the diode, then you are using silicon diode, then you can increase the temperature to 125 degrees Celsius. And it's better to handle the kit with care because it contains a heater, it contains some delicate thermometer, and it contains some circuitry, so it's better to keep it with you with as precautiously as possible. Thank you.